Welcome back. Today we're talking about the well-definedness of sin x and by extension the other trig functions. We're going to begin with the problem with Sohcahtoa. Many students begin their study of trigonometry with Sohcahtoa. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So let's first talk about what Sohcahtoa means, and then we're going to give a little bit of a critique of it, and then at the end a defense of it. Sohcahtoa says that sine x is opposite over hypotenuse. So that's a little bit vague because opposite of what, hypotenuse over what? It would be nice to fill in some details here. And so let's pause to fill in some details about what this actually means. So to be more specific, sine theta is the ratio opposite side length over hypotenuse length in a right triangle whose angles are theta, 90, and of course 90 minus theta because they have to sum to 180. Now, this is a true statement about sine theta, and it's useful for doing all sorts of calculations, but it's not merely a true statement about sine theta. It's the very definition of sine theta. And as a definition, it has a problem. The problem is it refers to a right triangle without telling us which one. And let me explain why this is a problem. It's a problem of well-definedness. So sine theta is the ratio opposite of our hypotenuse in a right triangle. In order to calculate sine theta, then, we need to have a right triangle. Let's suppose that we have an angle theta. Here's a given angle theta. From the angle alone, we cannot calculate sine theta. We need a right triangle in order to calculate sine theta. And so somehow along this angle, I have to build in a right triangle, which I've already prepared a little bit here. Now I have 3 points in a right triangle, and so I have the opportunity to calculate sine theta. Now I've already measured this out, but I want to indicate I need to measure the opposite side length here, and that'll be 6.3. I need to measure the hypotenuse length, and that'll be about 17.5. And then I have to calculate the ratio between them, 16.3 over 17.5, and that's about 0.36. So we'll conclude here that sine theta is approximately 0.36 for this angle. Now, okay, that's all well and good, but is that the correct calculation of sine theta? This definition raises a question: which right triangle is it appropriate to use? Should I care which one I use? Should I care how I draw it? This one I drew so that the angle pointed down. Often it's drawn so that the angle points sideways. Does it matter how the angle is represented? This is also the angle theta here. I guess I should put the label on the outside. This is the angle theta, and might I want to draw a right triangle whose angle theta is here and draw a different right triangle? It certainly is possible to do so. So why not do it? What will happen if I do? So I'm going to use this as a t-square in order to make a right angle here. And then I'll use it as a ruler too. So that will give me a right triangle. It's a completely different right triangle from the one that I started with. It has completely different side lengths from the side lengths that I began with, and therefore you might expect that it will have a completely different sine theta. And that would be bad because that would mean that sine theta was not just one thing, but many things. So I'm going to use this tape measure to ruler here to measure this. That's 25 inches. That's about 9 3/4. So here we get about 9.75 inches, 25 inches. I'm not even using the same units that I used above. This was centimeters. And then I calculate 9.75 over 25. And that's about 0.39. Now, you can tell from my drafting that none of my measurements were perfectly accurate, but this should give you pause. These are not in agreement. Now, we can blame measurement accuracy or calculation accuracy, or we can blame the essential problem of the definition itself, which did not tell us which triangle to use. Are these triangles really different in their ratios, or is this merely a problem of accuracy of measurement? That's the problem that we need to resolve here, and we need to do so logically and geometrically. So the answer, I don't want to hide the answer from you. The answer is I've measured a little bit inaccurately and I've drawn the triangles a little bit inaccurately, but I'm trying to make the point that this could in principle happen, that one triangle would give us one ratio opposite of our hypotenuse, and another triangle would give us a different ratio opposite of our hypotenuse. And then we wouldn't know what the sine of theta was, right? We've got the same angle theta. Sine theta is approximately 0.39. It's approximately 0.36. We don't know what's the real sine theta here. So this is the problem, and it's a problem of well-definedness. So the issue here, so the problem with this definition is, so we have to choose a right triangle arbitrarily in order to apply this definition. And in principle, it might matter which one we choose. That is, different right triangles might give us different calculations of the sine of theta, and that's what we need to demonstrate is not going to happen. At least, it's not going to happen in principle. Of course, when you measure anything twice, you get two different measurements. And when I drew these things inaccurately by hand, I introduced some measurement error. And so, when it comes down to measurement, you might get two slightly different measurements, but in principle, this should not happen. What we need to do is we need to state and prove the well-definedness here. So let's try to rescue ourselves from this situation. So the statement of well-definedness. So what does it mean for this thing to be well-defined after all? So if triangle ABC has, angle A equals theta and angle C equals 90 degrees, and triangle DEF has angle D equals theta and angle F equals 90 degrees. Now I'm going to relabel my triangles to reflect the hypothesis here before I state the conclusion. So this will be A, this will be B, and that will be C. This will be D, which notice is also equal to angle theta. This will be E, and this will be F down here. Notice that F and C are the 90-degree angles. So if these triangles have these conditions, then, well, I'd like to say sine A equals sine D, but instead of saying that, I want to spell out what we have tried to define sine A to be. So then we've tried to define sine A to be BC over AB. So then BC over AB equals, now how have we tried to define sine theta here? We've tried to define it to be EF over DE. So that will be EF over, I think I want to state this, DE. Yeah. In other words, the thing we tried to define sine A to be in this triangle agrees with the thing we tried to define sine D to be in this triangle. And so why would this be true? So if the triangles both are models of what you were supposed to do in Sohcahtoa, then the triangles will give you calculations of sine theta which are in agreement with one another. So why would that be? Let's see if I can justify it. And I'll give a justification up here. And the justification is very, very simple. It's nothing more than the proportionality feature of similar right triangles. So, so the proof of this statement here is, so if angle A equals angle D equals theta, and angles C and F are 90, then angles B and E are both 90 minus theta, and this is because they sum to 180. And this is the only number that can add these numbers and yield 180. And so we have triangle ABC is not congruent, but is similar to triangle DEF. So this is a statement of similarity of these triangles. We should always be very, very careful when stating that triangles are similar. it's not merely, the similarity statement between these triangles is not merely a statement that this triangle is similar to that statement, to that triangle here. It is an ordered statement. It is true that triangle ABC is similar to triangle DEF. And triangle DEF, of course, is the same triangle as triangle EFD, for example. But it would not be correct to say triangle ABC is similar to triangle EFD. The similarity statement is an ordered statement and has to match up the vertices in the proper order so that it expresses the similarity. So it has to match up the A and the D here both first in the naming order on the grounds that they have the same angle. B and E have to be in the same position in the naming order so that because they have the same angle, and C and F as well. So the similarity statement needs to be phrased very carefully. It's an ordered statement among those vertices. So this means that the triangles are similar, and if the triangles are similar, then they are proportional. I'm going to put an asterisk there. So what does it mean to say that they're proportional? It means that ratios of sides calculated between the triangles are always going to agree. So in particular, we have this ratio of sides, BC over AB, is going to agree with this other ratio of sides from the other triangle, EF over DE, so as needed. And what can we conclude from this? We can conclude the only possible explanation for the two slightly different answers here was measurement error in my calculation or drawing error in the way that I produced the figures. So thus sine theta is well defined. Now, if this is satisfying, great. And if it's not satisfying, I think I probably know why. If this explanation is not satisfying, it's because I've basically boiled down the well-definedness of sine theta to the proportionality of similar triangles. So this raises another question here. Here I'm claiming that if the triangles are similar, then they are proportional. And you should be asking, well, why are similar triangles proportional? Similarity is one thing. It's about the equality of the angles within the triangles. Proportionality is something completely different. It's a complicated statement about the equality of ratios between lengths of the triangles. Why are similar triangles proportional? That's kind of something that is left incomplete in this explanation, and I hope that you will look for that explanation in the next video. Take care.